Hi, my name is Peggy Folletta. I'm an education specialist here at Elkhorn Slough Reserve. We are by the visitor center, as you can see, and near the parking lot. But we'll be heading down to the trail soon to South Marsh Bridge. Over here on my right, you can see the Elkhorn Slough. We'll be collecting some water quality data while we're down there. Understanding Elkhorn Slough's estuary water quality is important for many reasons. The marsh and mudflat ecosystems support a very diverse food web, which could break down if the water conditions become unsustainable to its many species. Each species can survive in a very narrow range of conditions, and changes in the water may put stress on them. Discovering what may be causing the negative changes in the water quality will allow our scientists a chance to understand and mitigate the issues. Elkhorn Slough is a nursery to 55% of the fish caught in Monterey Bay. Water quality changes could impact these fisheries. Elkhorn Slough is a major stopping point for thousands of migrating birds who use it as a rest stop, where they can regain their strength and replenish their energy by feasting on the fish and invertebrates available. Marsh plants like the pickleweed and the eelgrass reduce the storm damage caused and help slow down the flow of the water before it reaches the land when there's a storm that's coming through. Healthy estuary habitats attract hikers and bird watchers who enjoy the beauty, diversity, and serenity surrounding them at Elkhorn Slough. So what are we waiting for? Follow me, and we'll head on down the trail to the water and learn to take some water quality measurements. Hi, we're ready to collect our water sample so we can take water quality measurements. We need a bucket with a long rope to collect the water. We also need to have our transparency tube right here, and our thermometer in the bucket, and our dissolved oxygen kit at hand, because those are the first measurements we'll be taking as soon as we retrieve the water sample. Why do we take these measurements first? Because we want to measure the clarity of the water, or transparency, before we disturb the water doing other tests. And temperature in the bucket of collected water may change soon after we collect the bucket, because it might be a really hot day or a cold day, and then we'll get an incorrect temperature reading if we wait a while and the bucket either heats up or cools off. The amount of dissolved oxygen changes when the temperature of the water changes, so we need to measure dissolved oxygen immediately as well. So here is the bucket with the rope. Here's a transparency tube, thermometer, and dissolved oxygen kit, and squirt bottle with distilled water. Hold on to the rope before you toss the bucket into the water. We don't want to lose it. Also, be sure the current is not too swift where you toss the bucket in, because you don't want to lose your student into the water. All right, so we're ready to take our water sample. Again, the first thing you need to remember is hang on to the rope. So I'm going to toss the bucket in, and I'm going to retrieve it. Now, the first bucket of water you take, you want to dump it back out, because you want to make sure the bucket is clean. And I'm going to dump it on the other side of the bridge. Now I'm going to take the actual sample we're going to use. So I'm holding on to it, the rope. I'm tossing the bucket in and filling it 2/3 to 3/4 full. And there we have it. So it's time to take our other measurements. I will demonstrate two techniques to measure transparency: the transparency tube and the Secchi disc. The transparency tube measures the clarity of the water at the surface, which is the water from the bucket. Light penetrates the tube from the sides. The Secchi disc measures light penetration through a column of water. Light reflected off the Secchi disc is passing through water from the surface. These two methods are not comparable. The measurements cannot be compared to each other. They can be compared, each measurement to itself, through time, over and over. So let's get to the measurement. We have retrieved a bucket of water, and now we're ready to take our transparency measurements. Remember, this is the first test to be done after water's retrieved, before students stir up the water taking the other tests. Suspended particles in the water behave like dust in the air. They reduce the visibility in the water. Plants, algae, and phytoplankton require light to photosynthesize. If transparency is reduced, the light will not be able to penetrate very far. So reduced transparency limits the depth at which plants can grow. Particles in the water scatter the light. Dark or black particles absorb most of the wavelengths of light, where white materials reflect and scatter most of the wavelengths of light. Tiny particles less than 1 micron scatter the light the most. So the degree of scattering depends on the amount, composition, and size of dissolved and suspended material. Dark water lakes with lots of calcium carbonate scatter blue-green light. Lakes with organic material in the water appear green or yellow. Rivers or estuaries with a high load of sediments are usually the color of the sediments. Ag land can be a major source of sediments. Farms on the hills around the slough will erode many sediments with fertilizers and pesticides during rainstorms. Colored organic material, or detritus, and plankton color the water as well. I will demonstrate two techniques to measure transparency: the transparency tube and the Secchi disc. The transparency tube measures the clarity of the water at the surface, which is the water from the bucket. Light penetrates the tube from the sides. The Secchi disc measures light penetration through a column of water. Light is reflected off the Secchi disc and is passing through the water from the surface. These two methods are not comparable. The measurements cannot be compared to each other, but they each can be compared through time, the same measurement over and over again, to see how it changes through the seasons and the years. So now we're going to be taking a measurement of transparency of the water using what we call a transparency tube. This tube was invented by the GLOBE program, and it is made up of two parts: a PVC end that fits over this fluorescent light bulb tube holder, which you can buy at stores like Home Depot. What you do is you mark on the bottom of the PVC the pattern that you see on a Secchi disc. On the tube, you mark off it by centimeters. So you can see here, perhaps, anyway, it's 5, 10, 15, 20. It goes all the way up to the top. The way the measurement works is you take a sample of water that you've just collected with your bucket and brought up to the in our case, this bridge, and then start filling the tube with water until the point where you can no longer see the pattern at the bottom. So I'll start, but I'm going to ask for a student to come up here and take this measurement, because there's one thing about this measurement: you don't want it to take it with dark glasses on, and since I have dark glasses, I'll get you some more water, and then you can be the one to add it until you can no longer see the pattern, or just barely. All right, so that's it. So what's the measurement? We go down here and we see that it is 29 centimeters. So this is a 29 centimeter reading of transparency. When you take a water transparency measurement on a sunny day, you need to remember to shade the transparency tube because we want the conditions to always be the same. That means always in the shade. It can't always be sunny because on non-sunny days, we don't have sun. So because we have sun today, I need to shade the tube when I take the measurement. So I have to use my body to shade the tube. So I have almost completed my measurement. I have a little more water to add, and I'm going to turn around and shade the tube as I finish the measurement. I can still see the pattern. Just a little more. It just disappeared. I have completed the reading. Now let's see, what was the reading? Let me look down here. It's 57 centimeters. So we're here on the South Marsh Bridge, and we're going to take a Secchi disc reading of the transparency of the water here by the bridge. Now, in order to take a Secchi disc reading, we need 3 items. We need the Secchi disc and the rope. We need 3 clothespins, and we need something that will float in the water so we can tell what the direction of the water is today. So I'm going to put the clothespins in my jacket pocket, and let's begin. So the first thing we have to do is we have a bridge here, and we need to determine which side of the bridge are we going to take this reading, because we do not want to put the Secchi disc in the water and have it go under the bridge. So I need to find out the direction of the water. So I'm going to drop this walnut shell into the water, and we'll see which direction the water is flowing. It's heading out to sea. It's heading out that direction. So I am on the right side, the correct side of the bridge. So we will now take the reading. So at this point, the Secchi disc is on the surface of the water, as you saw, and we have a reference point here where we're going to take all our measurements. If we were in a boat, we could just lean over the side and we would be at the surface of the water. But being that we're up on a dock, we have to have a reference point for the measurements. This is very convenient because the railing isn't going to go anywhere. So I'm going to take the first measurement, which is the distance to the water, by placing the clothespin on the rope. And that measurement is called distance to the water. Now I lower the Secchi disc until I can no longer see it. You notice the pattern on it was black and white, and I need to lower it to the point where I can't see the pattern. And I have dark glasses on. I need to take them off. This is something that should be measured with your naked eye. And I have found the point at which it is no longer visible. And this is when I take the second toothpick. I say that all the time. Clothespin out and mark the rope again. So that's the depth at which it disappeared. The next part of the protocol is to lower it even further, about 10 centimeters, and bring the Secchi disc back up until I can just barely see it. Right on that edge, and it's right there. Now you would expect it would be pretty close to that last measurement, and it should be. So I take the third clothespin. This is the Secchi disc coming back up until I can see it after lowering it. And then place the third clothespin. So we have completed our measurement. We have 3 clothespins. The first one was indicating the depth to the water. The one was the reading as the Secchi disc went down until it just disappeared. And then the third one is as we lowered the Secchi disc and brought it back up to where it just reappeared. Now, if the distance between these two is 10 centimeters or less, then the reading will be acceptable. We have to find the midpoint between these two clips, and that will be our Secchi disc reading point. So this is halfway between, so I'm going to take both clothespins off and mark the center. Now, the distance between this clothespin and the depth clothespin is our Secchi disc reading of depth. When you take a transparency measurement during a sunny day with the Secchi disc, there is one additional step you're going to need to take, and that is to shade the area where the Secchi disc goes underwater. And so you bring out either an umbrella or a piece of cardboard, and as you're lowering the rope, you shade the Secchi disc with the cardboard or the umbrella, because the measurement is different if it's in the sun or in the shade, and we can't count on sun all the time. So we need to, on sunny days, shade the area. We're going to take a water temperature reading here at South Marsh Bridge, but before we do that, we need to understand why we should take a temperature reading. Just knowing the temperature of the water in an estuary can give us a good idea of how healthy it is. One important thing we can tell from the water temperature is how much oxygen can be dissolved in the water. Dissolved oxygen is critical for the survival of animals and plants that live in the water. As the water temperature increases, the amount of oxygen that can dissolve in the water decreases. The temperature of the water also tells us what types of plants and animals are able to live in the estuary. All plants and animals have a range of temperatures in which they can survive and reproduce. For instance, salmon will only breed in temperatures below 18 degrees Celsius, whereas carp can survive in temperatures up to 32 degrees Celsius. If the water in the estuary is outside the normal seasonal temperatures, it is probably an indicator that something is adversely affecting the health of the estuary. Differences in water temperature cause the formation of distinct non-mixing layers in water, otherwise known as stratification, because the density of water changes with temperature. The stratification leads to chemically and biologically different regions in the water. Fresh water is less dense than salt water. So when it enters a salty estuary from the river, stream, or off a hillside from fresh fallen rain, fresh water will flow on top of the denser salt water. Water temperature is important for understanding local and global weather patterns. Water temperature changes differently than air temperatures because the water has a higher heat capacity. Water also helps to change air temperature through the process of evaporation and condensation. So now we're ready to take our reading, and we know why. To take a water temperature reading, we need a bucket with water that's been freshly retrieved from the body of water, and a thermometer that's been calibrated or checked to make sure that it's reading correctly. The protocol is to place the thermometer 10 centimeters into the water in the bucket and leave it there for 3 minutes. We want to make sure that we hold it from the top, not the bottom. The bottom, where the bulb is affected by the temperature. It is. Okay, my partner tells me it's been 3 minutes, so I'm going to check the temperature. Now, When you check the temperature, you need to make sure you don't take the thermometer out of the water because it will change to the temperature of the air very quickly. So just read into the water, read what the reading is. It is 14.5 degrees Celsius. Now we're not done yet. We have to wait one more minute just to make sure that we've waited long enough to get the actual temperature of the water in this bucket. And my partner says it's been another minute. So now let's see if it's the same temperature. It is. It's again 14.5 degrees Celsius. And so we can trust that reading. And I can take the thermometer out of the water. This reading, like all data that is collected by scientists, should be done in at least threes. In other words, we should get 2 other people to take water readings. We should get a fresh sample each time, and then we'll average the 3. We're going to do a dissolved oxygen test on the Elkhorn Slough water, but before we do, let's go over the reason for taking a dissolved oxygen measurement. Dissolved oxygen measures the amount of molecular oxygen, and that's O2, 2 atoms connected of oxygen dissolved in the water. It does not measure the amount of oxygen in the water molecule. The water molecule is H2O. We're not measuring the O in the water. Students often confuse the oxygen that is part of the water molecule, the O in the H2O, with the dissolved oxygen, O2. Just like animals that live on land, animals that live in the water need molecular oxygen to breathe. However, there is much more oxygen available in the atmosphere for animal respiration than in the water. Roughly 2 out of every 10 air molecules, that's 20% of the air, is molecular oxygen. In water, however, there's only 5 or 6 oxygen molecules for every 1 million water molecules. That's not very much. The amount of dissolved oxygen in the water determines what can live there. Some animals, like salmon or mayfly larvae, require higher levels of oxygen than other animals like catfish or leeches. Factors affecting the solubility of dissolved oxygen include water temperature, atmospheric pressure, and salinity. Cold water can dissolve more oxygen than warm water. As the temperature goes up, the molecules move around more quickly, and some of the oxygen molecules are jostled out of solution into the air. Water can hold less dissolved oxygen in higher elevations because there's less pressure pushing down to hold the oxygen molecules into the water. Solubility of dissolved oxygen also decreases as the salinity increases. Dissolved oxygen can be added to water by plants during photosynthesis, through diffusion from the atmosphere, or by aeration. Aeration occurs when water is mixed with air. Such mixing occurs in waves, riffles, and waterfalls. I just retrieved this bucket of water from the slough, and we're going to do a dissolved oxygen test. Before I do the test, I must put on my goggles to make sure that I follow all safety precautions. I have the instructions right here, and let's begin. I take my sample water container and I place it in the water upright like this so that it fills completely to the top with water. I tap it so that there are no air bubbles in the bottle. And I place the lid on it, turn it upside down, look for any air bubbles. I see none, so I can go on with the next part of the test. So I take the lid off, and I'm going to add 8 drops of manganese sulfate solution, and you should always check the labels twice. When you place drops into a solution, you should do it vertically. 1, 2, 3, 4, 5, 6, 7, 8. 8 drops of manganese sulfate, and then 8 drops of alkaline potassium iodide. Again, invert the bottle, 8 drops. 1, 2, 3, 4, 5, 6, 7, 8. the next step is cap and mix. So I will place the lid on the bottle, and mixing, this is the way you should mix the bottle. You're going to see a flock appear, which is sort of a cottony kind of liquidy material that turns a little bit orange, and let it settle. Now it's going to settle and, down to the shoulder of the bottle, and once it's clear above and it's settled to the shoulder of the bottle, then we can go on to the next step. And the next step is adding 8 drops of sulfuric acid, which has the red lid because it's one that you need to be very careful about. Now, this test has to be done immediately after you take the water out of the bucket and out of the slough, because the dissolved oxygen, if the water warms up, will bubble out of the solution and won't be a correct reading of what's in the slough. So let's see how our sample is doing. It's starting to settle. It's not there yet. You need to remember to bring a waste container to pour any wastes you have into it and take it back and dispose of it as your school recommends. Now, there's only part of this protocol that you need to do out in the field. And the next step will be the last step we have to do, and the rest of it we can complete back in the lab. And so, let's see, have we settled? Let's see how settled we are. It's settled up to the neck right now, and we need it to settle just a little bit more before we add the 8 drops of acid. If you have time, you can just complete the whole test here at the bridge, but I've been in conditions where it's pouring down rain. We're taking water quality tests, and we do not want to be out here in the rain any longer, so we go do the minimum. We need to get to the point where we fix the oxygen, which means we convert it into a chemical that we're going to measure so that we will get the right amount of oxygen in our reading. Okay, let's check. Okay, it has now settled. I can see clear on the top, so that indicates that we can now add the acid to the bottle. 8 drops again. 1, 2, 3, 4, 5, 6, 7, 8. I don't know if you've noticed, but the color in the bottle has changed. It becomes sort of a bright yellow or darkish yellow color, and then you are to mix it again. And it clears up. That flock we saw that was sort of cloudy looking becomes a clear yellow color. And that's the last step we need to do before we take it back to the lab and complete the test. And so at this point, we're going to do a titration. And we're going to take this sodium thiosulfate solution and our syringe, and we're going to fill the syringe with the solution up to the top line, which is 10. So I can see I have an air bubble. And we don't want an air bubble. When you get an air bubble, you push the solution back in and start over. I see an air bubble again, right there, and I think it's good now. Now I want to show you exactly where, there is a 0 line, 10's down here. When you fill it to 0, that's 10 milliliters. And so it's the bottom of the green, it's very flat, the bottom of the green cylinder. And so what we do is we take the lid off, we pour some of that solution up to the line, the 20 line. If you do make a mistake on the titration, you'll have some leftovers, so you could do it again. Just a little more. And it's right at 20. So I put the lid, the cap on here and the lid on here. And I start adding drops. And I swirl. It's going to become clearer and clearer. You want to wait until it's pale yellow. It's getting paler. And I would say just about there, that's very pale. And at that point, we take the lid off. We don't squirt any more of the solution out. We're just going to add more in a moment, but we need to add 8 drops of starch at this point. 1, 2, 3, 4, 5, 6, 7, 8. We put the cap back on and continue titrating until that solution turns clear. So I'll swirl it, and then we'll keep adding drops until it clears up. Okay, so now I have to read the titrator and to tell us how many milligrams per liter of dissolved oxygen was in the bottle. It is on, as you go down from 0 towards 10, you're reading 6 to 7. It's between 6 and 7, and it's the bottom of the flat green part, and each line represents 0.2. So this is 6.8 milligrams per liter of dissolved oxygen. And we are done. Now, before we go, we need to make sure that we have a waste container to put the waste in, and make sure we clean all of our containers, or all of our bottles out, so that the next person that uses the kit has a clean kit to use. And you should dispose of them in a manner that your school describes. You should use distilled water when you clean. And that completes the dissolved oxygen test. pH measures the acid content of the water. The pH scale runs from 0 to 14, with 7 being neutral. Anything higher than a pH of 7 is considered basic or alkaline, and anything lower than 7 is acidic. The pH scale is an inverse of the hydrogen ion concentration. So more hydrogen ions translates to a higher acidity and a lower pH. Each pH unit has 10 times more hydrogen ions than the next. For example, water with a pH of 4 has 10 times the number of hydrogen ions compared to a water sample with a pH of 5.0. A pH of 3 contains 100 times the acid content of water with a pH of 5. For this reason, small changes in pH could have significant effects in water quality. Most lakes and streams have pH values that range between 6.5 and 8.5. In fresh water, one can find waters that are naturally more acidic in areas with certain types of minerals in it, for example, like sulfides. Mining activity can also release acid-causing minerals to enter water bodies. Naturally occurring basic waters are found typically in areas where the soil is rich in minerals, such as calcite and limestone. pH levels are important because they affect most chemical and biological processes in the water. So pH influences what can live in the water. Aquatic organisms have specific pH ranges they require. Salamanders, frogs, and other amphibian life, as well as many macroinvertebrates, are particularly sensitive to extreme pH levels. Most insects, amphibians, and fish are absent in water bodies with pH below 4 or above 10. Carbon dioxide, which occurs naturally in the atmosphere, dissolves into the seawater, where it combines to form the weak acid carbonic acid. This breaks into hydrogen ions and bicarbonate ions. The bicarbonate ions also releases hydrogen ion. Oceans are well buffered by salts, but because of human-driven increased levels of carbon dioxide being added to the atmosphere, there's more carbon dioxide dissolving into the ocean, overwhelming its buffering capacity. The ocean's average pH is now around 8.1, which is basic or alkaline. As the ocean continues to absorb increasing levels of carbon dioxide through the atmosphere, the pH will decrease and the ocean will become more acidic. This declining pH can make it more difficult for ocean animals to thrive. I'm going to show you how to calibrate a pH meter. All instruments that Globe uses must be calibrated or checked to make sure they are working and taking correct readings. So for this pH meter, it requires 2 buffers. This is a pH 7 buffer. This is a pH 10 buffer. And a buffer is a solution that maintains the pH that it is. Like this one will always be pH 7. This solution will always be pH 10, and it's used as a reference. You can purchase buffers either in a solution form or in a tablet form. I purchased the tablets. This one says 4.0, and each tablet would be put in 100 milliliters of distilled water. Other solutions can be purchased that you don't have to mix. I have some distilled water here. This pH meter has been sitting in this water for a half an hour. There is an electrode that takes the reading, and it needs to be clean. So being in water for 30 minutes will dissolve anything that's on it. You'll see that there are 2 buttons, the on-off and the set hold. We won't use the set hold for this procedure. I'm going to turn on the meter. And it's reading. But to start calibrating, I need to push the off button, and it says off, and then it says cal. I had to hold it until it said cal. And at this point, I need to put it into a pH 7 buffer. So I'll take the lid off our pH 7 buffer and place it in the solution. It says REC, meaning it's received. It knows that the meter is in a 7.01 buffer. Soon it will change and tell me that it's ready. Like right now it says 4.01 use. And so at this point, I clean the pH 7 buffer off, blot it, and I'm going to place it in the pH 10 buffer. It says to put it in a pH 4 buffer, But the instructions say if you prefer to use a pH 10 buffer, go ahead, because it will recognize that it's in a pH 10 buffer presently. Right now it's wrong because it's not in a pH 4 buffer. We will wait patiently until it does recognize that it's in a pH 10 buffer. So it just changed to 10 and then it started reading normally. So right now, any solution I put it in, it would read a correct pH. It is considered to be calibrated. So it's changing now because this water is not at a 10 pH. I'm going to turn it off and I'm going to put the cap back on. You don't have to completely dry this, and you don't want to touch the electrode with your fingers. So put the cap on and take it out into the field, and then we can take pH readings. So that completes the process of calibrating the pH meter. I'm going to demonstrate how to take a globe pH measurement. This is a globe pH meter. This one has been calibrated as it should be before you use any instrument in globe. It should be calibrated, and this one was. The first thing you would do with your meter is to take the cap off. And you want to clean the cap with distilled water twice. So I'm spraying it. There's an electrode in here. We don't want to touch it with our fingers. There's also, on this particular meter, a temperature probe, but that's not required. So I'm cleaning it once, blotting it. We don't want to touch the electrode with our finger, but we want to blot it. It doesn't have to be dry, just blot it, because we don't want the water to mix with the sample water. Okay, the electrode, the meter is ready. Now, we have retrieved a bucket of water according to Globe Protocol, and I'm going to use this beaker to do the test in. I need to clean my beaker out with the sample water 3 times, and then dump it. 1, 2, 3. And then I'll take my sample. You may take this measurement directly from the body of water if it's safe to do so. I'll turn the meter on and I'll place it not touching the sides or the bottom of the container and wait until the numbers on our digital screen stabilize. And that may take 1 minute or so, somewhere around that time. So right now it seems to be stabilizing, right? It seems to be stable right now. It's reading 7.80 and it's stable. So I'm going to press the right button, which is the set hold button. So the reading will stay on the screen and I could pass it around to other people so they could write the data down. The reading for Globe, they want it to be taken to the 10th place. This meter goes to the 100th place. So we round to the 10th place to take the reading. So once we've recorded our reading, we can turn the instrument off. And then we can rinse it. Blot it to get the water sample off. So the next reading will have a clean meter. I will put the cap back on, and that's a pH reading. We're going to take a reading of pH using pH paper. pH paper is to be dipped into the water body and then placed against a color scale. and each color represents a pH level. And pH, as the background told you, is between 0 and 14. So the protocol requires that you use a container and that you rinse it out 3 times with the sample water. So that's 2, and then 3. And then it says to fill the container about half full. Take a piece of pH paper out of the container. And dip it into the water and then bring it out. That's what this type requires, is dip and then take it out. Some pH papers require you to leave it in longer, so just read the instructions on the type you're using. So now I match the color I have here to the color on my scale. And it appears that the pH is actually kind of between 6 and 7. So it's closer to the 6. So for globe, I would write pH 6. And then of course, you should have other students take 2 more readings with different samples of water. And then we average the 3, and that's our reading. Why do some types of plants and animals live in brackish estuaries while others live in the ocean and still others live in freshwater lakes and streams? One of the main reasons is the difference in salinities among these environments. Salinity is the measurement of the amount of dissolved solids in water. There are many different types of solids dissolved in water, but the most common dissolved solid is sodium chloride, table salt. Dissolved solids are often called salts. Plants and animals in both fresh and salt water have special mechanisms to maintain proper salt balance between their cells and the environment. Freshwater organisms are saltier than the water they live in. Freshwater tends to enter their cells and must be pumped out to keep the cells from swelling or even exploding. Animals such as fish in saltwater, are less salty than the seawater they live in. Many saltwater fish excrete salts from their gills and produce little urine so that they minimize the loss of liquids from their bodies. Animals that feed on organisms that live in the brackish or saltwater have developed ways to manage their salt content. For instance, seabirds and sea turtles have special salt glands to excrete the salt they take in with food and water. And pickleweed, that is the plant you see behind me in an estuary, and in this estuary specifically, here's an example, has a mechanism to transport the salt up their stems all the way to the tips, where it accumulates, dries, breaks off, and takes the salt away with it. The Earth's oceans average 35 parts per thousand salinity. Freshwater measures 0.5 parts per thousand or less. Coastal waters and surface waters of the ocean, far from shore, can be less salty than 35 parts per thousand due to freshwater input from land or rain, or more salty due to high rates of evaporation in hot climates. Some seas and lakes are also saltwater. Some examples include the Caspian Sea in Central Asia and the Great Salt Lake in North America. These water bodies are salty because water flows into them, then evaporates, leaving the salts behind. Freshwater bodies, however, have outlets so that salts move through them instead of accumulating. Brackish water is water that is saltier than freshwater, but not as salty as seawater. It is found in estuaries and bays where saltwater and freshwater mix. Estuaries are bodies of water that are partly enclosed from the open ocean and usually have a freshwater river source. Tides may affect the salinity of these water bodies. When the tide is high, the salinity may be higher than when the tide is low. Salinity may decrease when large amounts of fresh water are added during rain or snowmelt. Plants and animals living in these waters must be able to adapt to rapid and large changes in salinity. The young of these sea animals, such as baby shrimp and fish, live in brackish estuaries. Often, these young animals have the ability to survive in a wider range of saltiness than as adults. I'm going to go over how to calibrate or basically check the hydrometer to make sure that it's reading correctly, because you really can't adjust it, but all globe instruments either have to be checked or calibrated. So I have two hydrometers here, and they are used in the salinity measurement. So I have, these are new hydrometers. And here's one of them. I'm going to squirt some distilled water to clean it off. And I'm spilling a little, but that's life. Okay, I can lay it here on my clean towel, and then I will take the second one out and do the same thing. So they are new. We're going to check them. And the reason I have two graduated cylinders is I'm going to put two different solutions in them to check the hydrometer. One graduated cylinder is going to have distilled water. Now I poured distilled water into this beaker, and I'm going to put the distilled water, and I've cleaned the graduated cylinders with distilled water. And I am to fill them to within 2 or 3 centimeters of the top. So this one is pure distilled water. Now I have weighed out some salt here on our balance. I weighed out 17.5 grams of salt. The average salinity of the ocean is 35 parts per thousand. And so I have 500 milliliters here. So I only need half of the 35 grams per liter. And I have a half a liter, so I have a half of 35. So I'm going to put the salt into this graduated cylinder. And I will fill it. I'm going to grab a glove so that we can mix the solution. The salt will be completely dissolved in the water, and we will have a 35 part per thousand standard here to check our hydrometers with. So we're going to now take our readings, and the readings consist of a temperature of the liquid and a hydrometer reading. I will clean the instruments first to make sure they're absolutely clean. And so the thermometer, I'm just going to hang it here on the side and give it some time to equilibrate while we do the hydrometer reading. So I will also clean the new hydrometer with distilled water. And since we're placing it in distilled water, we don't have to worry about drips. Okay, I'm going to place this and let it bob up and down. And there's a scale on it that I will be able to read, but you won't be able to see it. A graphic will show you how this looks. And so I'll do the reading. The reading is 0.999. Now I think we could look at the temperature. The temperature is 16 degrees Celsius. So I have a scale here with the temperature across. 16 is here, 0.999 is here, And the specific gravity is 1.001. That's pretty darn close to 1.000, which would be what we would expect. So this hydrometer is functioning. We can use it. We can double check this hydrometer in our other solution. And it should be reading 35 parts per thousand, or we'll see what that is in specific gravity. So we're going to take, now remember, this thermometer is in distilled water, so we can just gently blot it a little bit. We'll place it in the other graduated cylinder, and we'll see how what the hydrometer reads here. Whoa, right away you can see it's much higher in the water than it was when it was in pure water, because there's a lot of salt in here, and the salt pushes the hydrometer up. And so based on the temperature and this reading, we can determine the salinity of the water. .025 is 34 parts per thousand. That's within 1 part per thousand. That's considered acceptable. So we double check this hydrometer and it's functioning. We would do the same procedure with the second hydrometer. If they are not functioning, I mean, if they're incorrect, we should do the test completely over and just verify that they are not reading correctly. Then you should send the hydrometer back, because you really can't adjust it. I'm going to demonstrate how to use a refractometer to take a salinity measurement. It isn't a globe instrument at this time, but we use it here at Elkhorn Slough Reserve, and a lot of people use them. And so I want to demonstrate how to properly use the instrument to measure salinity. We have retrieved a sample of water using Globe Protocol into this bucket. And so I have cleaned, and I'll wipe off the glass surface here, which is part of a prism. There's a prism in here. We'll talk about that later. And then this will spread the water evenly across the prism, the top of the prism. So I'm going to take a sample, kind of just maybe 3 times, squirt it, put a few drops on the glass here, and then spread it evenly across the surface. And then I will look through the eyepiece to take the reading, and there's the top half or more is blue and the bottom is white, and based on how much salt is in the water, it will cause the light to bend more if there's more salt and less if there's less salt. It's kind of like when you put a stick into a swimming pool, and at the water level it looks like the stick bends. That's because the density of the water is different than the air. Well, salt water has a different density than fresh water, and so the prism bends it based on how much salt is in it. And then we have a scale in the eyepiece to take a reading. I read the right-hand scale. It's 35 parts per thousand, and maybe, hopefully you got an idea of what the reading looks like. And we do that in triplicate like we do all globe, well, like we do, we here do it in triplicate like we do with globe instruments. We wipe it down. We have some distilled water over here, so that we can clean the dropper, so the next time we don't have residual salt in it. And then we can, we have also a waste container. So as we clean the instrument, water will go into the waste container. And then we'll wipe the surface, the two surfaces off, and we're ready to put the instrument away. There is a calibration to this instrument, like all instruments. And I'm not going to demonstrate that now, but the instrument comes with the information on how to calibrate it, so you should follow that. So even if you can't submit it to Globe, it's a good instrument to use to get salinities. I'm going to show you how to take a salinity reading using a hydrometer and a thermometer. This is a sample that was collected yesterday in the estuary, was labeled and taped, as all samples should be if you're going to bring them back into the lab. And so I'm going to break the seal and pour the sample into the graduated cylinder. And you fill the graduated cylinder until the water level is about 2 or 3 centimeters below the top of the graduated cylinder. It really doesn't matter the precise number of milliliters of water. Just you want to be able to read a hydrometer reading, not a volume reading. So that's about 2.5 centimeters. Since the temperature takes a while to equilibrate, I'm going to put the thermometer into the graduated cylinder, and we'll check back later to get the temperature. And then we will use the thermometer that has been checked so we know it functions correctly, and we're going to take a reading. As it's bobbing up and down, you'll see a graphic on the screen that shows you how this measurement can be read. It'll be more of a close-up. Any salt added to water is going to make the hydrometer move higher because there's more salt that pushes up on the hydrometer. So, all right, I have a chart here. Across the top is the temperature, and down the side is the specific gravity. And so basically I'll find the specific gravity and the temperature, and we'll find out what the parts per thousand the salinity is. So let's begin. All right, so I'm going to read the hydrometer. It's 1.025. 1.025 is the specific gravity. And so I'm going to look down to 1.025. So my finger's on that. And that by now the thermometer is probably reading the correct temperature. And that temperature is 16 degrees. And so 16 degrees is here. So I've got 16 and 1.025. And the reading is 33.9 parts per thousand. And that's what we would record. We should have other groups collect other samples and repeat this, so we have at least 3 readings that we can average and report to Globe. And that's how you take a salinity reading. Fresh water has many natural impurities, including salts or minerals dissolved in the water that we cannot always see or smell. As water comes in contact with rocks and soil, some minerals dissolve in the water. Other impurities can enter a body of water through runoff or wastewater releases. If water contains high amounts of dissolved salts, it may be harmful to use for watering crops. We call the amount of mineral and impurities in the water total dissolved solids, or TDS for short. We measure TDS as parts per million, or ppm. This tells us how many units of impurities there are for 1 million units of water by mass. For water we use at home, we prefer a TDS of less than 500 parts per million, although water with higher TDS can still be quite safe. Water used for agriculture should have a TDS below 1,200 parts per million, so sensitive crops are not harmed. Manufacturing, especially electronics, requires impurity-free water. We use an indirect measure to find the TDS of water. One way to measure impurities in the water is to find out if it conducts electricity. Pure water is a poor conductor of electricity. When certain solids, typically salts, are dissolved in the water, they dissociate and form ions. Ions carry an electrical charge, either positive or negative. More ions in the water mean the water will conduct electricity better. The electrical conductivity meter measures how much electricity is being conducted through a centimeter of water. If you look at the probe end of the meter, you will see that there are electrodes 1 centimeter apart. Conductivity is measured in microsiemens per centimeter. This is the same unit as a micromole, which some of you may know from physics. It's the inverse of ohms. To convert the electrical conductivity of a water sample into the approximate concentration of the total dissolved solids in parts per million in the sample, you must multiply the conductivity microsiemens per centimeter by a conversion factor. The conversion factor depends on the chemical composition and of the dissolved solids in the water, and it can vary between 0.54 and 0.96. For instance, sugars do not affect conductivity because they don't form ions. The value 0.67 is commonly used as an approximation. TDS in parts per million equals conductivity, microsiemens per centimeter, times the factor 0.67. It is better to use a conversion factor that has been determined by your water body instead of this approximation, since the impurities between the water bodies can vary greatly. Drinking water with a conductivity of 750 microsiemens per centimeter will have an approximate concentration of total dissolved solids of 500 parts per million. Pure alpine snow from remote areas has a conductivity as low as 5 to 30 microsiemens per centimeter. There are several manufacturers and models of conductivity meters. Some models may measure conductivity in increments of 10 microsiemens per centimeter, others in increments of 1. If your model measures in increments of 10 microsiemens per centimeter, you will have to calibrate it as closely as you can to the standard solution. Your accuracy and precision will never be better than 10 microsiemens per centimeter. The meters need to be calibrated before testing the water sample. This can be done in the classroom shortly before going to or while at the hydrosphere study site. I'm going to show you how to calibrate this conductivity tester. I have instructions from the kit I received it from, and so whatever type you use, instructions will come with it to explain how to calibrate it. In my case, I needed some standard solution that is precisely at 1413, that is 1,413 microsiemens per centimeter. And I have poured some of this solution into container 1 and into container 2. So they are pure 1413 or 1,413 microsiemens per centimeter. And so once we calibrate it, that's what this will read, and will match that number. And it will be calibrated and usable to measure conductivity in freshwater solutions. First, I take the cap off. I have my distilled water, and I rinse the electrodes. And then I blot it dry not completely dry. Don't touch the electrode with your fingers. And then you place it into the first solution. In case there's a little bit of distilled water still on the meter, it will come off in the first solution. I'm going to turn the meter on because that's the first step in calibrating. And then I need to press the cal button on the right side, and you can see, I don't know if you can see, but it says cal. Once it says cal, you can put it into the second solution. The second solution should now be pure 1,413 microsiemens per centimeter. And so it takes a minute until the instrument reaches that number, and once it does, it'll flash and tell me that it is calibrated. And now it's telling me that, yes, I received the solution. REC. I know you can't see that, but it says received. And it's flashing and saying, okay, it's being calibrated right now. In a short minute, probably, it says it's calibrated. And now, any solution I put it in, any freshwater solution, I should get a correct reading. Now, I'm going to clean the conductivity solution off with the distilled water, turn off the instrument, blot dry or close to dry. It's okay if there's a little moisture on it when you store it. And it is calibrated and can be used on samples. Oh, hi. I was a little distracted. There's a lot of life in this pond here. Pretty cool. I'll have to look at that another time. We have a protocol in Globe to look at the invertebrates in the fresh water. And by the way, we're doing fresh water here. This is a pond. Today our test is to look at the conductivity of the water. So I have a conductivity meter here, but the protocol requires us to check the temperature of the water before we take the conductivity. So let me do that. So I take a sample, and I'm putting just a regular thermometer in and just taking a water temperature. If the water is too cold, then the meter may not be very accurate. Also, if the water's too hot. So the range at which is acceptable to take the reading is between 20 degrees Celsius and 30 degrees Celsius. So we'll see if our water qualifies. If not, we're going to have to take a sample indoors and let it heat up or cool down until the temperature is within that range. And then we can take the reading. The thermometer is reading 13 degrees right now, and it's not moving. Looks like we're going to have to take a sample and take our reading indoors. So let me get my container, which I've labeled already, just in case we needed it. A polyethylene plastic bottle that should be filled completely. And we want it filled to overflowing, as we don't want any air bubbles in it. And then we need to seal it with tape so that we will know if it's been opened or not. Because when we sample it, we want to make sure it hasn't been opened. So now we're back at the lab. We were doing the conductivity test and discovered that the water was too cold for us to be able to do the test because the water needed to be at least 20 degrees Celsius and it was 13 out there in the field. So we bottled up our sample. It's right here, and the tape tells me that it hasn't been unsealed. So now I will unseal the sample and test the temperature first before I take a conductivity reading. And just a reminder, it needed to be full all the way to the top. So as long as this goes above 20, but not all the way to 30, we're in business, and we can take a conductivity reading. Just to let you know, we're going to have 2 samples, and we will be putting the probe into one sample and then transferring it to the second. And it's now stabilized at 21 degrees Celsius. And so this water temperature is acceptable to do our test. So I need to place some of the sample into beaker 1 and some of our sample into beaker 2. I'll take the probe, the conductivity probe, and I'll clean the electrode, or the 2 pieces of metal. And I will blot it dry. Well, not dry, but just blot it. I'll turn the meter on, and there's a screen giving us a reading. And I will place it in the water up to about 3 centimeters deep and just kind of stir it around because I might have some fresh water still on it, some distilled water. And so this way I'm going to get all the distilled water off and kind of mix it with the first sample, and then I move it directly to the second. And then I wait for it to stabilize to take the reading. It has stabilized. The reading is 395 microsiemens per centimeter square. Now I'll turn the reading off, clean the electrodes again, so that the next person that uses it will have a clean instrument. And remember, every globe reading should have at least 3 samples taken and averaged, and that's how you take a conductivity reading.